We were discussing in the previous lecture the concept of trajectory planning, because any robot is designed to execute a certain specific task that will entail that the end effector move through certain specified motions through specific points with some velocities and desired accelerations if need be. So we started discussion of how we will plan the motion of individual joints such that you will be able to actually get the desired motion at the end effector. So we call this the trajectory planning. And when you look at the trajectory planning, we have also, just to recapitulate what we discussed earlier, we talked about the way in which the task specification naturally happens in the joint, in the world coordinate frame, and the lower level control of the motion of the robot manipulated actually takes place in the joint coordinates, because you have the actuators at the individual joints, you have the sensors at the individual joints, and so the controlled motion could more conveniently be achieved in the joint space. So we were mentioning in the previous class about how the task space or Cartesian space is related to the joint space, okay. So we discussed it through an example of a planar 2R manipulator and showed how what are the intricacies of mapping these two on one onto the other, and then showed that these are related, and so we could go ahead doing the manipulation of the trajectory planning etc. in the joint space. So this is what we were doing in the previous class. When we look at the joint space trajectory planning, we look at a particular way in which we would like to do that, in the sense of for a specified initial position I to a final position j or some other position j with specified velocities and position at these points. So theta I dot, theta j dot being given, we showed how a cubic curve fit can be achieved in the joint space. Okay. So this is the stage where we were, but the problem we identified in at the end of the previous discussion was that if we had to follow this type of a strategy to be implemented in a real manipulator, then if you have between the initial and final positions, if you have say n via points, then the user needs to give n plus 2, because for the initial position 1 and the final position the second. So n plus 2 sets of data on position, velocity data. There were two issues that we raised with respect to this aspect, that is, he has to give a large set of data, that is one aspect. The other aspect is that he has to give a what is known as a kinematically consistent data. What do we mean by kinematically consistent data? We have, for example, we were talking about the task space to joint space manipulation, okay, or mapping the task space to the joint space. Now, if the user specifies certain positions and certain velocities for the end effector in the task space in the world coordinates, it is perhaps possible when he specifies it for n plus 2 points, at some positions in the world coordinates, the end effector's velocity that he desires may not be achievable through any finite velocities of the individual joints. These are what are known as near singular positions, we said, and so we cannot probably achieve certain desired velocities for the end effector. So when we say that it has to be kinematically consistent data, what we really mean is that it should be such that for finite joint motions we will be able to achieve the required end effectors velocities at the desired positions. So this is something that we need to keep in mind. So the user has to keep track of these aspects and give an appropriate data. Okay. So in terms of user interface, we mentioned that therefore this is not probably the most desirable way of doing it, because user shouldn't have to give a huge set of data, a complex set of functions with respect to time and so on and so forth. He shouldn't have to worry about the kinematic consistency of the data or otherwise. So what rather would be convenient for the user is to specify that user would love to specify simply, user simply specifies that you go through an initial position, and when I say position, he may specify the initial positions at the velocity at that position and so on and so forth, and the final position. Okay, because these are things that are of importance to him. But in between, at the via points, he may only specify the positions of these via points, okay, and he may allow the system to choose appropriate velocities. Okay, so position specified at these points, position specified velocity to be chosen by the system. Okay, so this choice eliminates any requirement of kinematic consistency from the point of view of the user. Okay, so he needs to simply specify the initial position and the final position and a set of via points, and the system will choose appropriate attainable velocities, maybe based on the smoothness of motion through these via points. The system will choose that appropriately and then plan the entire trajectory. So let's look at some aspect of how we will do this type of a motion. So let's look at, for example, a typical case of 3 points specified, 3 positions or 3 points specified. I am calling them I, J, K. These need not be the initial and final positions. They are just 3 general points, and what we are trying to say is that at I and K, to be representative, at I and K, position and velocity specified. Okay, but at J, which is the via point or intermediate point, he specifies only the position. How do we fit a trajectory through these type of problems? Okay, so what it means is that you have the time, you have the theta, you have one position here, another position here, and a third position here. This could be I, this is J, this is K. Okay, so we need to find a smooth trajectory through these points. Okay, so let's look at how we will do that. One easy way to visualize extending the idea of the cubic segment that we just now talked about is to say that I will fit one cubic polynomial between I and J and another cubic polynomial between J and K. Okay, so let us say that the durations of the motion are also specified. Let this be Tij and let this be Tjk. So Tij refers to the time taken moving from I to J, and Tjk refers to the time taken moving from J to K. And at I and K, position velocity being given, and at J only the position is given, velocity is to left for the system to choose. So let's look at how we will solve this type of a problem. So between Ij, so I will say two, first of all we are talking about 2 cubic curves or segments. Okay, 2 cubic segments to be fit between I and K. So Ij is one segment and Jk is another segment. So what I am going to do is to say that theta of tau is C0, C1 tau, C2 tau squared plus C3 tau cube, and here theta of tau is again say some B0 plus B1 tau plus B2 tau squared plus B3 tau cube, where tau is a local time frame. Like we introduced in the previous lecture, tau here will vary from 0 to Tij. Here tau will vary again from 0 to Tjk, because that is a local time frame with reference to that specific cubic segment of motion. Okay. So now the constraints are that theta of 0 for this segment should be the initial position, or the theta I. We have also said that the velocity is specified here. So theta dot of 0 at the beginning of the motion in the ij segment is the prescribed value of the velocity at the position I. So theta I dot, and the position at j is specified. Therefore, at Tij, the profile should be such that at the time Tij, when tau is equal to Tij, theta should be theta j. Okay. Similarly, on this segment Jk, theta of 0, when tau is 0, that means you are referring to the position j now, because the time axis is a local time axis moving from 0 to the time period for that segment. So theta of 0 should be theta j. Then theta of Tjk is theta k, and theta dot of Tjk is the given velocity at the point k. So let us look at now that two cubic curves between Ij and Jk, and each cubic curve has 4 coefficients, C0, C1, C2, C3, B0, B1, B2, B3. So totally we need to determine 8 coefficients for the cubic curves. So among the 8 coefficients to be determined, so we need to get 8 conditions or equations to be solved for those 8 unknown coefficients, and therefore what we are writing down here is only 6. We need to generate 2 more, and those 2 more equations are generated based on the fact that at position j, velocity has not been prescribed any value. We want a smooth motion. Okay. So I would say that the velocity and acceleration at the position j be continuous. Okay. So these 2 conditions I will use to generate the necessary 2 equations at the position j. So at j, okay, we want continuity of velocity and acceleration, and that gives us the 2 equations that we are looking for. Now what is the continuity of velocity and acceleration means what? Whether we theta dot Ij, I would say, that is coming from the ijth segment at Tij should be equal to theta dot Jk at 0. Similarly, theta double dot Ij segment at time Tij should be equal to theta double dot Jk when evaluated at tau is equal to 0. These are the 2 conditions that we want. Okay, let us look at how these would turn out to be. So what this means is that in terms of theta of tau being C0 plus C1 tau plus C2 tau squared plus C3 tau cube in the ijth segment. Therefore, theta dot of tau is C1 plus 2 C2 tau plus 3 C3 tau squared, and theta double dot of tau is 2 C2 plus 3 C3 6 C3 tau. Okay. This is for the Ij segment. Now similarly for the Jk segment, theta of tau Jk, and this is Ij. Okay. Theta of tau is B0 plus B1 tau plus B2 tau squared plus b3 tau cube, and so theta dot of tau is b1 plus 2b2 tau plus 3b3 tau squared, or theta double dot of tau is 2b2 plus 6b3 tau. So, we now have the relations for the velocities and accelerations. We will just stipulate the necessary smoothness constraints, that is the velocity and acceleration be continuous at the position j. So, let us see how those relations between the coefficients turn out to be. So, theta dot of velocity continuity at j, that would mean that theta dots be same. So, therefore, we are talking in terms of C1 plus 2C2 Tij plus 3C3 Tij squared. This is the velocity coming from the ijth segment, that should be equal to the velocity coming as calculated from the jk segment, that is simply b1, because tau is equal to 0 for this segment. Acceleration continuity at j will mean that you have 2c2 plus 6c3 Tij squared is equal to 2b2 Tij. Okay. 2c2 plus 6c3 Tij squared is Tij is 2b2, because tau is 0 and tau is equal to Tij here. Okay. So, you have additional two equations as you can see here, and therefore, you have the necessary equations to solve for all the 8 coefficients. 2 cubic segments, so each cubic segment has 4 coefficients to be determined. So, you have the 8 equations. So, therefore, 8 equations for 8 coefficients C0 to C3, B0 to B3. Okay. So, you would see therefore, that the user has specified at this stage only the initial position velocity, final position velocity, but at all the intermediate via points he has only required the point in which position in which the end effector should move, and the system has chosen appropriate velocity such that the velocity and acceleration are smooth at the interface point via point j. Okay. So, we are able to do a curve fit essentially using again cubic polynomial segments, okay, with between Tij 0 to Tij in the ijth segment and jkth segment. So, 2 cubic polynomials in this case. In general, if we have n number of points, then how would we use this type of a strategy? So, if we have an initial position, in general, this type of a strategy, how do we carry out? In general, you have initial position velocity are specified, final position velocity are specified, and in between you have specified n via points. So, we talk in terms of therefore totally 1 plus n plus 1. So, n plus 2 points, and so we are talking in terms of n plus 1 cubic segments to be fit. So, n plus 1 cubic segments to be fit, and each cubic segment will require 4 coefficients, and so we are talking about each cubic segment needs 4 coefficients, has 4 coefficients, and therefore 4 into n plus 1 coefficients to be determined. The moment you have 4 into n plus 1 coefficients to be determined, you also require 4 into n plus 1 equations to get the corresponding coefficients uniquely. Four into n plus 1 equations are required. Now, how do you get these 4 into n plus 1 equations? It's essentially same as what we discussed with the example of 3 general points, okay, expanded to any number of n number of intermediate or via points. So, at the initial position and velocity constraint, velocity conditions, you will have 2 equations, right, initial position and initial velocity. Similarly, the final position and final position's velocity conditions will give you 2 more equations. Okay. Now, at each intermediate position, at each via point, you have position condition. Position condition is that if whether you come from the left segment or from the right segment, the position has to be the prescribed position. So, you have actually 2 equations. Okay. And then velocity continuity and acceleration continuity, you have therefore 2 more equations. One equation, this is one equation and this is another equation. Okay. So, you keep on writing these equations. So, you would see that if there are n points, therefore, n via points give you 2 plus 1 plus 1, 4 n equations. Okay. And you have here 2 equations for the initial position and 2 equations for the final position. So, total number of equations will be 4n plus 4. Okay. That is what you will require. So, total number of equations is 4n plus 2 is 4 into n plus 1. These are the number of equations required. So, therefore, all the coefficients can be determined. Right? All the coefficients can be found, and you will be able to, given any strategy, any set of initial and final positions, velocities, and a set of any number of via points, without the user having to tell you what is the velocity, based on the simple heuristic that the smoothness of motion demands the velocity and acceleration be continuous at all the intermediate via points, you will be able to fit the entire trajectory from the initial position to the final position, making use of the cubic curves. Okay. Now, if you look at what we have discussed, it is for one particular joint motion. So, if you have multiple joints, then you have to do this type of thing for each and individual joints motion. Okay. So, that combined motion of all the joints will give you the required end effectors motion. Okay. So, keep that point in mind. While we are talking about an individual joint's motion being planned, we need to do this type of trajectory planning and generation for all the individual joints, and so the number of coefficients that we are talking about here will be increasing based on the number of joints in the actual robotic manipulator. Okay. So, keep this perspective in mind. Now, if you look at this particular discussion that we have had so far, we have used the cubic polynomials. Now, why only cubic polynomials for curve fitting? It is very simply the lowest degree polynomial that allows you to ensure velocity and acceleration continuity. Okay. So, that is the advantage. Why cubic? If you ask the question, why did we emphasize cubic curves being used? Okay, why cubic segments? The simple answer is that it is an easy, the lowest degree polynomial, and hence the easiest to work with, lowest degree polynomial okay, that ensures velocity and acceleration, because these are the quantities of importance to us as engineers. Velocity and acceleration are very important parameters of motion. So, velocity and acceleration continuity is guaranteed. Okay. Now, therefore, it is, since it is a lowest degree polynomial, it is obviously the easy to work with. We have seen how we can determine all the coefficients in a very systematic manner, generating all the equations that are required to obtain all these coefficients. We will be able to fit any such cubic trajectory. Now, is it that we cannot use a higher order polynomial? No, it is not really like that. We can use a higher order polynomial if we need to. Okay, so we can use, in fact, we can use even lower or higher order polynomials. So I will discuss both these aspects so that you don't have fixation only on the cubic curve fits. So we can use even lower or higher polynomials. Higher so we will see how, for example, okay, I could use a higher degree polynomial. When we are talking in terms of a higher degree polynomial, how did we come with the idea of using a cubic polynomial? If you recall, when we looked at the problem of fitting a trajectory to an individual joint's motion, I talked about moving from a position I to a position j, where I said at the position I and at position j, you have prescribed position as well as velocity information, which you need to satisfy. So therefore, for the joint, we talked about 4 conditions to be satisfied, and therefore any polynomial that requires 4 coefficients, we would be able to fit. So we talked about a cubic curve fit. That is how we got the idea of using a cubic curve fit. Okay. So we were introduced the idea of using a cubic curve fit from the point of view of having to satisfy the position and velocity constraints at the position I and at position j. So we are talking about this. If we were to use a higher degree polynomial, so naturally we will have to use higher degree polynomials if we have more constraints to be satisfied. Supposing I am trying to talk about move from position I to j such that you have theta I dot and theta I double dot, similarly theta j dot and theta j double dot. That means accelerations also are specified, suppose. Okay, just as a hypothetical case to present the argument in front of you, if you have prescribed positions, velocities and accelerations at both the position I and both position j, then you have 6 conditions. When you have 6 conditions, you can actually generate equations for determining 6 coefficients. When we say 6 coefficients, we are talking about theta of tau, therefore can be C naught plus C1 tau plus C2 tau square plus C3 tau cube plus C4 tau 4 plus C5 tau power 5. Okay. So we can use actually a higher degree polynomial if we have additional constraints specified in terms of the accelerations also at the points I and j. Okay. So this is one case wherein you could use actually a higher degree polynomial. But acceleration specification will require again, as we mentioned, the idea of a user interface, the user has to give you more data, more requirements, more specifications. So it is not necessary that we use a higher degree polynomial only when there are acceleration specifications. Even otherwise also we may actually use a higher degree polynomial. So I will now highlight to you one such case where we would like to use a higher degree polynomial in terms of trajectory planning for an individual joint. Suppose you look at the application of a pick and place. Okay. So if you look at the example, this is an example of a pick and place kind of application. Then we are talking about, say, a surface on which a certain object is placed. Okay, you have a certain object placed on the surface. Okay, and you have from somewhere the gripper or the end effector is approaching this. Okay, when you look at the type of, so this is a gripper or end effector approaching the object on a surface. This is a support surface. When it is being picked up, you wouldn't like the gripper to press into the support surface. That means the nature of motion, approach motion, should be such that it doesn't press into the support surface or it doesn't really crash into the support surface. So you may want to control the process of picking up the object by specifying actually a certain point slightly away from the initial position on a normal to the surface. Okay. So if the surface is here and the object is on the surface, I am trying to capture this object, grasp this object, I might actually specify a position slightly away from this on a normal to the surface, so that my takeoff from the surface is appropriately controlled. Okay. So I might actually specify from the initial position a slightly separated position on a normal to the outward normal to the surface. Similarly, at the other end, when I am actually placing the object on another supporting surface, I would specify a position slightly away from the final position. So if I am trying to place the object on a surface, support surface, then I can place it, I can specify a position slightly away from the final position on an outward normal to the surface, such that I settle down into that position and then gradually place the object onto the final support surface. So you might actually specify the motion required, okay, in terms of the end effector's motion, that there is an initial position, there is a position slightly separated from the initial position which is on a normal to the surface, and then there is a final position, but just before the final position you place yourself appropriately, so that you will gradually settle into the final position. So this can be converted through the kinematics of the manipulator into a requirement on the joint space motion. Okay, that we have discussed in the previous class through an example of a 2-hour manipulator, how the kinematic relationships can be written down and then you can obtain the joint motions required. So therefore, if you look at this type of situation where you are talking about a pick and place application, where you would specify initial position and then say takeoff position, let us say, or okay, so that it is slightly separated from the initial position with a particular along the normal to the surface, and so you can control the takeoff, approach velocities and so on. Similarly, you will have a final position, but before that you will have a where you are going to place it. Let me say that it is a set down position, and finally you are talking about a final position. Okay, so that the supporting surface or the interaction with the environment is in a desired manner. So, if you do that, then for an individual joint, this might actually mean that you have something like this. So, you have an initial position, let us say I, and a position slightly separated from this, so let us say here, and a final position that you want to go here, and a position slightly before this. So, you may want to actually fit a smooth curve through this. So, you have these positions I, F, lift off or take off position, okay, and then the set down position. Okay. So, I is initial, L is referring to lift off or take off. I am not using the letter T here because T could be confused with time. So, we could call this as a lift off position. S is a set down, and F is the final position. Okay. So, these are the 4 points. For such a type of trajectory planning, a method that is commonly done is to follow what is known as a 4-3-4 trajectory. What we mean by 4-3-4, as you would have guessed, it refers to the degree of the polynomial curve fit that is used. Okay. 4 means that you have actually IL, you use a 4th degree polynomial, okay, and you use between L and S the lift off position and cruising up to the set down position, you use a cubic, that is 3rd degree polynomial, and final set down to the final position you use again a 4th degree polynomial. This is another common strategy that is employed in trajectory planning for joint space motions. Okay. So, how do we get the corresponding equations? Say for example, if you again define local time frames, okay, you define local time frames tau. Let us say that I to L takes TIL time, then L to S should take you, the duration is also specified, it is say TLS, and S to F should take you a duration that is specified is TSF say. So, in each case the local time frame tau will go from 0 to TIL, 0 to TLS, 0 to TSF. So, we are talking in terms of a 4th degree polynomial to be fit in this segment, a cubic polynomial to be fit in this segment, and a 4th degree polynomial to be fit in the final segment. So, we are talking in terms of 3 specific segments being used. Okay. So, from I to L, we can say that theta IL of tau is say A naught, because it is a 4th degree polynomial, A1 tau plus A2 tau squared plus A3 tau cube. Okay. Now, so therefore, 4th degree polynomials we will have A4 tau 4. So, 5 coefficients to be found. to be able to generate this strategy. L to S is cubic, so theta Ls of tau is B naught B1 tau plus B2 tau squared plus B3 tau cube. So 4 coefficients to be found. Okay. So we are using a 4th degree polynomial, so 5 coefficients here from between I and L, and we are using a cubic polynomial between L and S, therefore 4 coefficients. And similarly again from S to F we are using a a 4th degree polynomial. Theta Ls of tau is C naught plus C1 tau plus C2 tau squared C3 tau cube plus C4 tau power 4. So we are talking in terms of again 5 coefficients here. To be determined. So therefore in all 5 plus 4 plus 5, that is 14 coefficients to be determined. So I need to generate 14 equations based on the different types of constraints that I need to satisfy. Then I will be able to actually do this kind of a curve fit and plan the trajectory appropriately. So 14 conditions required. Okay. Now where do I get these 14 coefficients conditions from? Okay. So you look at the motion that you are asking for. So there is an initial position I, there is a final position, there is a set down position, there is a take off or lift off position, and corresponding time durations. So we need to generate 14 equations for fitting a 4-3-4 polynomial through this. Okay. So that we will get a smooth motion from the initial to the final position, with the objective of actually the pick and place operation of interacting with the environment and the support surface is satisfied. So we are talking about the initial position at I. You can have initial position specified. So position, so theta IL of 0 is theta I. Theta dot IL of 0 is theta I dot. These are prescribed position velocity conditions. So similarly theta double dot of IL, the polynomial that you are 4th degree polynomial that you are fitting at tau is equal to 0 at the initial position I should be theta I double dot that has been prescribed. Okay. So we have, let us say, 1, 3 conditions. Okay. Okay. Let's look at the final position again on a similar line at the final position F. Okay. You have theta SF of say T SF should be equal to theta F, that is prescribed, and it should have certain velocity theta dot final, theta double dot, that is the accelerations are also prescribed, and therefore you can have these. Okay. So this I will number them as 4, 5, 6. Okay. So this is the prescribed position, velocity and acceleration at the final position. These velocity and acceleration could be actually 0 depending on the application, particular application that you are talking about. Okay. But in general, any prescribed velocity and acceleration can be satisfied. So we have now 6 equations. So we need to generate 8 more equations based on the intermediate positions L and S. Okay. So, at L, so just for your benefit, let us look at the time graph again. We are talking about the lift off position here, this set down position here, and then the final position there. Okay. At L, okay, so you have theta IL, okay, that is for this segment. At TIJ, TIL should be theta L, that is specified, because the time duration is specified and the position is specified, where which is slightly away from the initial position and along a normal to the support surface. Okay. Theta LS at 0 should be theta L, and we can talk of theta dot, and that is velocities and accelerations should be continuous at the position. So, theta dot of IL at TIL should be equal to theta dot of LS at 0. This is velocity continuity, and theta double dot IL at TIL is theta double dot LS at 0. So, this is equation 7, 8, 9 and 10. These two being velocity and acceleration continuity conditions. Okay. And these give the prescribed position of the lift off point conditions. Okay. So, we have 4 conditions at the point L. So, we have 10 equations so far. If we write 4 more equations at the position S, then we will have the necessary equations to solve for all the coefficients. So, at S again, F, S, L, I. So, at S, theta LS of TLS should be the position that we have prescribed. Theta SF at time t equal to 0, because we are talking about a local time frame from S to F again. So, at time t equal to 0 for this cubic segment here, okay, or a quartic segment here, at time t equal to 0, your position should be what has been prescribed. Similarly, the velocity and acceleration continuity conditions, okay, and theta double dot this is again velocity and acceleration continuity. So, you have 11, 12, 13, 14. So, all the equations can be solved, therefore, all the coefficients of 4, 3, 4 trajectory can be found. So, we are talking in terms of a commonly employed strategy of a higher degree polynomial along with a cubic polynomial. So, 4, 3, 4 can be, all the coefficients can be found out in this manner. So, if you look at the process of trajectory planning in the joint space, the way we have discussed it, you will see that conceptually it is actually fairly straightforward, simple way of satisfying the prescribed conditions, and depending on the nature of constraints, positions alone or positions velocities or positions velocities and accelerations or continuity on the velocity and acceleration at certain intermediate positions, so that you will have smooth motion. You will be able to choose the polynomial type that you would be able to fit for the individual segments, and correspondingly you can determine the number of coefficients in the polynomial. Okay. So, the trajectory planning in principle is a process of curve fitting to satisfy the prescribed conditions on position, velocity and acceleration if need be, okay, and the smoothness of constraints and so on and so forth, velocities and accelerations. So, this is another commonly employed strategy, 4-3-4 strategy. There are other strategies that you would find commonly employed, but the basic concept remains the same. So, we need not really discuss each and every strategy, because once you understand the basic philosophy of trajectory planning in the joint space through one set of curve fits, you will be able to extend it to other types of trajectory planning strategies. So, instead of having say a 4-3-4 for the same kind of motion, you can have actually say 3-5-3. Okay, that means that you could have a cubic fit between I and L, and then a fifth degree polynomial between L and S, and then a final cubic segment to take off, towards the approach position. So, it is possible that you can have different types of strategies, and all of them revolve around essentially satisfying your simple motion constraints on position, velocity and acceleration. Ultimately, you want to move from one position to another position with sufficient smoothness of motion. That is essentially what you need to keep in mind. So far, you should remember, to recapitulate the point that we mentioned in one of the previous lectures, is that you have not talked about how much acceleration can actually be obtained at the joint. Is there any limit on that? Okay. So, such constraints have not been taken into account. I am purely doing a kinematic or a geometry of motion kind of analysis and trying to fit the polynomial curve fits to satisfy the constraints. But we have not talked about whether or not a particular acceleration can actually be achieved with a particular joint actuator sitting there in real time, in real world, okay, because each actuator has a certain finite capabilities. Similarly, we have not looked at the aspect of other dynamic issues, like for example, we talk in terms of compliances at the joints or compliances in the links and so on and so forth. So, manipulator dynamics could also affect this. Okay. So, these aspects complicate the trajectory planning further. So, we would not be able to discuss those, but what we would try to discuss is a couple of other issues related to how we could use very simple strategies similar to these cubic curves and higher degree polynomials. But as you would notice, with cubic curves and higher degree polynomials, the more the number of terms in the polynomial curve fit you use, so many equations have to be generated, so many equations have to be solved for, and so for a multi-joint robotic manipulator, it could become quite a task. So, we would rather have, is there any possibility of simpler strategies for trajectory planning? So, we would rather ask such questions and try to address whether I can fit even simpler, rather than trying to make it more complicated, even simpler strategies for trajectory planning. So, we will discuss that, see what are the other issues related to trajectory planning in the next class.